All right, good morning again. We're going to start the respiratory system. So this I may post it earlier because it takes a while to upload them, but this won't be till after the exam. So again, Monday, what is it, the 13th? That's when the exam will be posted. I'll probably leave it up for that week. So I'll have these up there, but these are for the next exam. Now, respiratory system, it's not too bad. It's got a few gas laws in there. We'll have a few equations up, but mostly with the equations, we look at them qualitatively, not quantitatively. That's not going to punch a lot of numbers in, just a few. But first of all, the function of the respiratory system. Of course, the respiratory system, the lungs, nasal cavities, all the airways, all it does, it takes air from the atmosphere and brings it in, and then takes that air and moves it back out. So it's just like a big bellows. Actually, mammals have a really pretty cruddy respiratory system. It's inefficient, but that's all right. There's so much oxygen in the atmosphere, we don't need a real efficient one. But two things that the respiratory system does. One of them, you pretty much know, I imagine. The respiratory system takes oxygen, I'll just call it O2. It's a molecular gas in the atmosphere. Takes oxygen from the atmosphere, brings it in, and allows it to move into the blood. Of course, the respiratory system has to work in conjunction with the circulatory system. Just bringing oxygen from the atmosphere to here wouldn't do you any good. What about those, poor little cells at the end of your big toe? The respiratory system just brings the oxygen into the blood. Once it's in the circulatory system, that's how it's distributed. So we're going to take oxygen from the atmosphere, get it into the blood. And do keep in mind, oxygen in the atmosphere makes up about 21% of atmospheric gases in the free atmosphere. Most of the gas is 21% oxygen. One of the functions. The other function, of course, we produce carbon dioxide. CO2 is carbon dioxide, is a metabolic waste. In fact, both these gases, you looked at them before. The reason you need oxygen to get it into those metabolic pathways. Remember, glycolysis, Krebs cycle, electron transport chain. The only reason you need oxygen is to get it into that electron transport chain so it can act as a final sort of hydrogen or electron acceptor. It's the only place you use the oxygen is in the mitochondria. That's why you need it, so you can keep that high metabolism. So you need the oxygen for those metabolic pathways. In a similar manner, if you remember those metabolic pathways, when you break down something like the carbohydrate glucose, you produce carbon dioxide. Carbon dioxide is a toxic gas. You have to remove it. So the respiratory system brings in oxygen, feeds it into those metabolic pathways. As the metabolic pathways produce carbon dioxide, that gets moved to the lungs, diffuses into the lungs, you exhale it. So that one, we've probably known that since we were in, kindergarten. The other function, not as well known, but the respiratory system also controls the pH of your blood. Blood pH is about 7.4. And again, pH is one of those variables you have to maintain at a set point, because if your pH goes up too much or down too much, it interferes with your enzymes. It breaks hydrogen bonds. Your enzymes don't work. You don't have much of a metabolism. And if you don't have much of a metabolism, you're dead. So the respiratory system is going to control pH. Now, the way it does it is it's a little weird. We know pH is a measure of the hydrogen ion concentration in solution. I don't see any hydrogen ions up here. So how can the respiratory system do anything with pH? Well, you probably looked at this last semester, but if you remember, if you take carbon dioxide and you add it to water, keep in mind, water is always going to be in excess in your body. You're like a 80% big bag of water. If you take carbon dioxide, add it to water, it will undergo a reaction. It is a spontaneous reaction, although there are some enzymes that speed it up, as we'll see. The carbon dioxide will recombine and you will produce this substance here, H2CO3, which is called carbonic acid. It is a weak acid. Carbonic acid will dissociate. Of course, this reaction can go either direction. It's an equilibrium reaction. And carbonic acid will dissociate into some hydrogen ions plus HCO3 minus. My sheet's in the way here. Which is bicarbonate ions. That's a negative charge there. So there are your hydrogen ions. So as we'll see, The respiratory system can control carbon dioxide, and by definition, if you add carbon dioxide to water, it will produce hydrogen ions. Carbon dioxide is an acid. So one of the uses of the respiratory system, one of its functions, is to control the amount of carbon dioxide in your blood that's used to control pH. In fact, as we'll see, because there is so much oxygen in atmospheric air, you don't even breathe normally to control oxygen levels. There's plenty. What actually controls your breathing? It's the carbon dioxide. You get rid of it if there's too much, or you breathe a little slower if you need to retain it a little bit. So that's how we control the pH. Now, what we're going to look at next, I'm going to switch videos, and we'll just start, because it's kind of it for the functions. Now what we're going to do is look at the parts. We'll kind of start at the nasal cavities and nostrils. It's the inlet for the air. Normally, we do a lot of mouth breathing, but should go through the external nares or nostrils. We'll just follow the pathway there from the external nares through all the kind of parts, going down through all the various airways and passageways until we get to the functional portion of the lungs, the alveolar sacs, and that's where we'll stop, because that's it for the anatomy. Now, once we're done with that, we'll actually have to look at the circulatory system again, and we'll look at the role it plays in distributing that oxygen once it diffuses into the blood. So we'll look at hemoglobin a little bit and its binding characteristics, that sort of thing. Now, while we're looking at the respiratory system, we're going to be dealing with gases. They behave a little differently than the other states of matter we commonly look at, solids, liquids. So we'll look at probably three, we'll call them gas laws. These are our rules. Again, a law is just a theory with a lot of evidence. You don't get a ticket if you break it, but we've never found any ability to break it, so we call it a law. That'll help describe some of the characteristics of gases. The first one I'll mention today, because it'll come up in the next part of the lecture. One of the characteristics of gases is its volume. Again, liquids, solids, their volume is pretty much fixed. If you change your pressure a bit, their volume doesn't change. You got a gallon of water, it doesn't matter what's happening outside, it's a gallon of water. You got a gallon of rocks, it's a gallon of rocks. It doesn't change. Gases, however, they have no fixed volume. So because their volume would change a lot, it causes some issues you'll have to keep in mind. We start looking at, concentration gradients, things like that. And the first sort of law we'll mention, it's the simplest. It's called Boyle's law. Boyle's law, it's actually part of the ideal gas law you might have had in chemistry, but we keep it a little simpler. Boyle's law describes the relationship between pressure on the gas and its volume at a constant temperature. Again, temperature is going to affect volume as well. We're just going to keep that constant so we don't have to worry about it. So Boyle's law says that if you change the pressure on some amount of gas, its volume will change. There's a little equation you can use. The equation is usually written P1 V1 equals P2 V2. The way to look at these, P1 is the initial pressure on the gas. V1 is its initial volume. That has to be equal to, these second two values are the final pressure on the gas times the final volume. Let me give you an example. Let's see if I can do it here. Let's say you have a syringe. Here's a syringe. There's a syringe body. We'll put a little plunger in here. So this is a syringe. We've taken a needle off, so it's safe. And it's open to the atmosphere. So there's a pressure in the atmosphere. Typically, we'll use as a standard sea level pressure. That means, if you stood at the average sort of tide level at the ocean, sea level, there's a column of gas above you going up for kilometers. Gravity's pulling that down and it's crushing your body, basically. It's exerting pressure. That is sea level pressure. The units we'll use are millimeters of mercury, which we've already looked at with the circulatory system. This is a pressure you should probably just commit to memory. Sea level pressure is 716 millimeters of mercury. Now, of course, that changes. It's not fixed. That's sort of an average. We're not at sea level. That means in Kentucky, we're a few hundred feet above sea level. Some of the atmosphere is below us. It's no longer crushing us. The pressure on average would be slightly lower here. Weather fronts that move over, high pressure, low pressure, they talk about, when you look at the weather reports, that changes the pressure because it changes the density of the air. And that's going to affect the force it has, kind of squishing on your body. But 760 is kind of a constant, standard or average sea level pressure. We'll use that. So let's say that's what we are. Now this syringe is open. There's no air moving in, no air moving out. It's going to reach equilibrium. So the pressure inside here will also be 760. Now, syringes, they're calibrated, right, in milliliters, let's say. If we look at this syringe right here on the barrel, it says 5 milliliters. So what we have is a volume of gas here, 5 milliliters. That's this one, 5. Pressure on the gas is 760. Now what I'm going to do, imagine you put your finger over the syringe. So it's sealed. It's got no needle on it, it's safe. So you close it. You haven't changed anything else yet. There's still 5 milliliters in there and 760. But now we're going to take that plunger and we can pull it down. We can take a syringe, you stick it in something, and you pull it. So let's say, I can't erase here, but let's say we pull this plunger down to this point right here. And now we look at the side and it says we have 10 milliliters. All right, we doubled the volume. What happened to the pressure? No air could get in because we have our finger on the end. So it's the same amount, same number of molecules, but it's taking up twice as much space. So we got the volume, that's V2, the final volume is 10 milliliters. What is the pressure in that syringe? Now think about it. Put your finger on a syringe, hold it there, pull the plunger down. When you let your finger off, does air blow out or does it suck in? The syringes, they suck when you blow out that plunger. That's how they can draw blood out. So the pressure is going to be lower. How much lower? You can do the math. We got some pressure times 5. That's 760 times 5. You got the second pressure we don't know, times 10. Well, let's divide by 10. Divide by 10. I can drop that to 2. So 760 divided by 2 is 350, 60, 70, 80. P2 equals 380. Is that on the board even? Barely, if you can read it. Basically what happened, I doubled the volume on this amount of gas. If you reduce the volume or you double the volume, the pressure is going to be reduced by 1/2. 380 is half of 760. You can do the same thing. If I squish this up so it's only 2.5 milliliters in there, what would be the pressure? It would be double that. What is that? 14, 15, 20. That's Boyle's law. Basically, if you double the pressure on a gas, closed system, no air can get in or out. You double the pressure, the volume will squeeze down to 1/2. So if you had a liter balloon and you double the pressure on it, it would squeeze down to 1/2 liter. If you had a liter balloon and you reduce the pressure to half what it is in the atmosphere, it would expand to a 2-liter balloon. That's all Boyle's law is. So the volume isn't fixed at a constant temperature. It depends on the pressure. Volume be up, volume be down. It can change. So that's Boyle's law. Just have some idea of how it works. I think it's fairly intuitive, but if you need to, plug your numbers into the equation. I'll always give you 3. So it's algebra, you just solve for the missing one. Take care. I'll add this to the next part of the video, which will be kind of going through nasal cavities, concha bones, pharynx, that sort of thing. Take care. All right, we'll start with a little bit of the anatomy of the respiratory system. I'm using the lab model. This is a lab model of the head. We've got a couple of them in lab, just because these are probably the images I'll use on the lab practical. Now, as previously mentioned, respiratory system basically has 2 functions. One, we know it's to obtain oxygen and eliminate carbon dioxide, which are used and produced by those metabolic pathways you looked at last semester. That's why we need the oxygen, and that's where the CO2 comes from. The other function is control of pH. The respiratory system controls pH by controlling the plasma levels or the blood levels of carbon dioxide. Now, what we're going to do with this is we're just going to go through some of the parts. All right, respiratory system. Now, humans, we're pretty much mouth breathers, but the respiratory system sort of evolved to breathe through your nostrils or external nares here. So we're just going to follow the pathway of air from its inlet, the external nares, down to the functional portion of the lungs, which we'll see in a moment is called the alveoli. Now, external nares here, they just act as the inlets. There might be some guard hairs in there, that sort of thing, to keep flies and, peas and gravel out of your nose, but it's basically just an inlet. So the air moves in through the external nares, and it goes into this large sort of hollow cavity in the bones of your face. These are the nasal cavities. There's 2 of them. There'd be a septum right in the plane of the picture here, separating into the left and right nasal cavities. And inside the nasal cavities, you see a number of these curled, kind of shell-shaped bones here. These are the concha bones. The one at the top is the superior concha. It's just kind of curled like a little C. The middle one is, surprisingly enough, the middle concha bone, and that's the inferior concha bone.
The spaces underneath them, that's where the air would flow, are the meatuses. So if that's the inferior concha bone, that's the inferior meatus. Inferior concha bone, kind of the inferior meatus is underneath it, and so on. Let's see. All right, now the nasal cavities, not only do they act as a conduit for air, they have a couple of other useful functions. First of all these surfaces, if this were real, would be covered with mucous membrane. It's a glandular epithelia, secretes a lot of mucus. It's very well perfused, has a good blood supply, so that would cover the cavity. And it would also cover all these curved concha bones, the septum, the works. So good blood supply, very sort of secretory, a lot of mucus. Now, what the nasal cavities will do, other than just act as a conduit for the air, is they modify the atmospheric air before it gets down to the functional portion of the lungs. The functional portion of the lungs is a bunch of little microscopic sort of bag-like structures. They're called alveoli. They are incredibly thin. The membrane separating the air in the alveoli from the blood into pulmonary capillaries is like 0.2 micrometers thick. It's almost soap bubble thin. Very delicate, very easy to damage. And it's thin, so you can maximize rates of diffusion. All it's made up of, that layer, it's called the respiratory membrane. It's a layer of simple squamous epithelium, the thinnest epithelial cell we've got, lining the alveoli. Simple squamous epithelia, the endothelial cell lining the blood vessel. And they have a fused or a common basement membrane. So it's very thin. You don't want debris or harsh material down into that part of the lung. It will damage it. So as atmospheric air moves in, it's often got some extreme characteristics. For example, the atmospheric air can be quite dry. Relative humidity might be 15% in a room. It can be quite low. Granted, not in Kentucky in the summer, but in some places and in some seasons, it's very dry. You don't want to snuff that dry air down into the lungs, because as we'll see, the inside of the lungs, because they're only a cell layer thick, they have to be moist. They are wet. If you take in a lot of dry air, you'll evaporate that water, damage or kill the cells. Lungs won't work. You'll suffocate. So as the air passes through the nasal cavities, these concha bones actually make the air spin around a lot. And all these concha bones, well, in humans are not terribly elaborate, they still add a lot of surface area. And all these surfaces, remember, are covered with mucous membrane, which is secreting mucus. Mucus is mostly water. There's some protein in it. It's a little stickier in water, more viscous. But the water, it's got a high water content. So as that air circulates around, going through all these meatuses and around all these bones, it gets humidified. By the time the air reaches the functional portion of the lung, it's saturated with water vapor or at 100% relative humidity. That prevents you from drying out the lung. So that's one. The nasal cavities help to humidify the air, add moisture. Number two, atmospheric air can be really cold. You go up around Fairbanks or even Missoula, Montana. Some years it might be 50, 60 below zero. You spit, it freezes before it hits the ground. Nasty. Well, you don't want to snuff that really cold air in the lungs. You kind of freeze dry them. So as the air moves around all these surfaces in the nasal cavities, remember, the mucous membrane is very well perfused. You're bringing warm, core temperature blood and running through all these surfaces. It's acting like a radiator. Heat is exchanged. So that cold air, as it moves through here, by the time it reaches a functional portion of the lung, it's at body temperature. And finally, I'll explain this on the board a little later, but it acts as a filter. Now, it doesn't look like much of a filter. I mean, you could take a pencil and kind of stick it through your nostrils and back here into your pharynx. It wouldn't filter out anything, much bigger than marble. That's about it. The way it works is interesting. It's like a centrifuge. As the air spins around, any particulate matter that's denser than the air molecules tends to smash into the surfaces. Again, a particle wants to go in a straight line unless some force makes it turn. Particles with density don't take turns very well. They slam into these surfaces as the air is accelerated and spins around all these concha bones. And of course, they're covered with mucus, which is sticky. It's like flypaper. So as the air comes in here and spins around these concha bones, it acts like a centrifuge. All the particulate matter slams into the mucus, and there are ciliary tracts that will then carry this mucus back to your throat, or you can spit it out or swallow it or whatever you want to do with your dirty mucus. So nasal cavities, they do act as a conduit for air, but they humidify, they warm, and they also filter the air. That's why, of course, with the human, then we do all this mouth breathing, we bypass that. That's why we get probably more respiratory problems than many other mammals. So that's the nasal cavity. A couple other things associated with the nasal cavity. The lacrimal gland up in your eye produces tears. There's a little duct that goes from the lacrimal bone. You looked at it, I think, as a lacrimal fossa last semester. But that lacrimal gland has a drain. There's a lacrimal duct running from the orbit up here somewhere down. And right here, they've cut away part of the inferior concha bone. That little dot there is representing the opening to the nasolacrimal duct. That's partly why your nose runs when you cry. The tears are draining out here and they're going in your nose. Makes it a little soupier. So that's a connection. Another thing, you remember sinuses from last semester? These are just hollow air-filled spaces surrounded by bones in your face. They do a couple of things. They reduce the weight of your head, so you're less likely to get, neck injuries, that sort of thing. And they also act as resonating chambers. That's why you sound a little funny when you have a cold. But there's a problem with these. We'll talk about it in lecture, but it's Boyle's law. Gases do not have a fixed volume. If you change the pressure, this gas will expand or contract. Well, if this gas tries to expand, it's all surrounded by bone. If the pressure drops outside, you drive up a mountain or something, you don't want your head to explode. Okay, your head wouldn't really explode, but it would cause a lot of pressure, damage soft tissue. So anytime you have an air-filled space surrounded by bone, there's going to be a way for the pressure to equalize with the atmosphere. You might have looked at last semester with the middle ear. It's the same problem. Middle ear is coming in a little further down though. But all these sinuses also have little tubes connecting them to the nasal cavity, which is at atmospheric pressure. So if the gas in here tries to expand, it can leave out that little tube in your nasal cavity, which is atmospheric, to relieve the pressure. If this volume starts to drop, pressure is reduced, gas can move in the tube to equalize the pressure in the sinuses. That's why when you get a cold or something and you plug up those tubes, you might get a sinus headache or something as the pressure builds up in here. All right, that's it for the nasal cavities. The next part of the respiratory system back here, this constriction here, that's sometimes called the internal nares, internal nostrils, if you will. Remember, you can pick your external nostrils or nose. You don't really pick your internal nares, too far back. But back here is the end of the nasal cavity, so internal nares we could call it. And this next part, it's a tube, runs from the internal nares all the way to about here where the respiratory and digestive systems diverge. So air, you want to go in this tube, more ventrally. Food, you want to go dorsally down the esophagus to the digestive tract. So this whole tube right here, it is a common passageway for both the digestive and respiratory system. That is the pharynx. Now, in a cat, we're just going to call it the pharynx, but in a human, we've got 3 different regions of the pharynx, and they're based on landmarks. The cat's landmarks are going to be completely different because our larynx is a little funky compared to the cat's. But we'll separate this pharynx into 3 parts. The first part, we'll go from the internal nares. And this thing right here, this is a palate. You looked at it a bit last semester. Hard palate is supported by bone, maxilla there and palatine bone. And then there's a fleshy projection out the back. That's a soft palate, not supported by bone. The palate just separates the nasal cavity from oral cavity. The end of the soft palate is kind of one of the landmarks. So if we go from the internal nares to the end of the soft palate here, so this region right here is called the nasopharynx. Then, the next part, if we go from the end of the soft palate, this little blue thing sticking up here, that's the epiglottis. It's a piece of cartilage, part of the larynx. That's kind of a second landmark. So if we go from the soft palate to the epiglottis, kind of the area right behind the oral cavity here, the mouth, that's the oropharynx. And then finally, if we go from the epiglottis to about this point here where the digestive and respiratory systems diverge, that's the laryngopharynx. So those are the 3 parts of the pharynx. Some structures you'll note in the pharynx. This is one of the areas where we have tonsils. There's only 2 of them indicated on this model. There's a mass right here. Just looks like that granular white stuff on this model. There's one right here at the side of the palate. There'd be another one on the back of the tongue, but it's not here. It's removed from this model. Tonsils, they're basically part of the lymphatic system. They're a little like lymph nodes, except they don't have a connective tissue capsule. They have all these pits and crevices in them. These are basically there to initiate an immune response. If you think about it, short of puncturing the skin, where do pathogens come in? You either inhale them or you eat them. So you got a lot of lymphatic tissue right there so you can initiate an immune response fairly quickly. The set of tonsils up here in the nasopharynx, those are the pharyngeal tonsils. They may also call them adenoids. You've got 2 on either side of the arch of the palate, which would be right here, over here, and over here. Those are the palatine tonsils. If you stick your tongue out and push down to the tongue depressor and go, you might see those. The third one would be located on the back of the tongue here. You got this nasty, it looked like a little brain-like looking structure on the back of the tongue. If you bounce a flashlight off the mirror, push your tongue down to the tongue depressor, you'll see this nasty thing with breakfast and lunch bits hanging in it. That would be the lingual tonsils. So those are associated with the pharynx as well. palatine tonsils in the nasopharynx, pharyngeal tonsils in the nasopharynx, palatine tonsils on the edge of the palate, and lingual tonsils on the back of the tongue. Now, once we leave the pharynx, this is where the digestive and respiratory systems will diverge. I'll go over the larynx next time. I think the only other thing I want to mention, this little brown like slit opening on this model up in the nasopharynx, that's the opening to the auditory tube or eustachian tube, which you may have also looked at last semester when you were looking at the ear. That's a way to equalize the pressure between the middle ear, which is an air-filled space, and the atmosphere, because the pharynx is considered atmospheric. So we'll stop there with the pharynx, and I'll pick up larynx next time. Take care.